is Vivian Eagar, and this is my presentation investigating magnetic field connections and solar flare events by me with assistance from my mentor, Dr. Rebecca Purvis. So to start with some background information, a solar flare is a common weather event observed in the sun's atmosphere. Solar flares are a sudden change in the configuration of magnetic fields that result in EM radiation emission. They can be classified by their X-ray brightness on a letter scale of 5 classes, A, B, C, M, and X. Only C and higher flares are picked up by space weather monitors. Solar flares can also have an impact on Earth, affecting technology such as radios and satellites. Solar flares are often identified at the time at which they occur and the active region they occur in. An active region is an area on the sun that has a strong magnetic field, which makes it prone to events like flaring and coronal mass ejections. For this project, we're looking at a specific type of flare. A sympathetic solar flare is when one flare triggers another flare in a different active region. Sympathetic solar flares have been identified and studied in the past. However, what exactly causes the events to be linked and how to predict when they happen is the focus of this project. In particular, the idea that the magnetic fields of the sun are connecting the flares or letting them communicate. Another important thing to define is field lines. Field lines are representations of the direction and strength of a field, in this case a magnetic field at a point. In the context of the sun, this typically shows how the magnetic field continues out from the photosphere. Field lines can either be open or closed. On the sun, if a field line is closed, it connects back into another point on the sun. If it's open, it extends out into space without reconnecting to the sun's surface. These field lines are important because they give a visual of how the sun's magnetic field moves, which helps identify aspects of solar weather, like solar wind, or structures that appear on the surface of the sun, such as coronal holes or loops. In this project, to keep a limited scope, the goal was to identify at least 2 recent, possibly sympathetic flare events and investigate the structure of the magnetic field before flares, developing 3D models to create visual representations of the active regions and magnetic field structure, as well as identify evidence of energy flow and EUV observation. For this project, we decided that it would be best if we looked only at flares not tied to any other solar events, such as coronal mass ejections, so we could focus specifically on flares. In solar flare prediction models, sympathetic events and structures like coronal holes are often not taken into account, so this project aimed to look more into how these factors could be relevant to improving prediction models as well as general understanding of sympathetic events. We can see this example of a prediction model showing the percent chances of an M or X class flare within 24 hours at the active regions currently visible on Earth, from Earth. This is not from today, but you can still see the number, locations, and then their percent chances of M or X class. So for this project, we started with the Community Coordinated Modeling Center's Donkey database of notifications, knowledge, information, and ISWA integrated space weather analysis tools. Donkey's website allows for sorting through data of solar events based on the time frame. But for a more controlled search, I downloaded all the solar flare data from this past year. I wrote a Python script to sort what I downloaded based on if there were any linked events, again to keep things simplified, and if the flare happened close enough in time to other flares to be considered possibly sympathetic. This sorted data was then exported into a spreadsheet. From this sorting, I was able to identify the events we analyzed for this project. Photos of the sun are often taken at varying wavelengths to highlight different features. To observe possible links between the events, the tools HelioViewer and the AIA's Atmospheric Imaging Assembly's Fieldline Viewer websites were used to get visuals. To pull the image data at the most granular intervals available, I also used the JSOC Joint Science Operations Center Look Data feature. JSOC allowed for 12-second intervals, which is the shortest available. However, there were data gaps and the files downloaded as FITS files, which aren't really easily viewable. Using the image editor GIMP and a plugin called Batcher, the files could be converted. However, a significant portion of the times we were analyzing were still unavailable. HelioViewer only had 36-second intervals, however the data gap issue was not present and allowed for features like viewing the difference between images, so it seemed like the more efficient choice. Here are some examples of the visuals. First is a screenshot of the AIA Fieldline Viewer website displaying SDO HMI data, showing the magnetic field strength and polarity near the base of the solar atmosphere. The lines show this magnetic field as it extends past the lower atmosphere. Second, we have a video compiled from the FITS files I pulled from JSOC, again of STO HMI images. This video spans from 1908 to 1930 on the date April 26th of this year, and is at the wavelength of 171 angstrom. This wavelength is best for showcasing coronal loops and also shows the strength of the magnetic field but closer to the edge of the sun's atmosphere. With the brightness brightest parts denoting the strongest parts of the magnetic field. This same wavelength is also seen in the third video, which is pulled from HelioViewer, but instead shows the time 1910 to 2010 on the same day. This video is also utilizing the SDO HMI images. The fourth video is also from HelioViewer, displaying the running difference of the third video, showing only the changes between each frame. 3D modeling started using Onshape, a CAD software, but was later shifted to Blender, which felt like a much better fit and ended up being what was used for the final models. For the models, the information we wanted to display was the sun's magnetic fields, which are often represented by a magnetogram image that shows the strength and polarity of these fields, using a black and white system. To convert this to 3D, the magnetogram was used as a displacement map, with the white values raised and black values lowered. Important field lines were also modeled. This meant that when 3D printing the model, all of the information could be conveyed by the shape itself in a more tactile way. I also have images, but here are examples of the 3D prints, so you can see the magnetogram. While working in Blender, I had made a few Python scripts to automate things like active region marker placement, and thought it might be helpful to put it somewhere accessible. I ended up making a website with JavaScript 3D that pulls directly from SDO and Donkey to display flare information on the web. A few examples of what I coded for the website include an image cropper that cut out black space to keep images from SDO the same size, and an auto-updating caching system for the Donkey data to keep the load times relatively fast. This website will be viewable on the N3 site. The events found were on April 26th and June 5th of this year. The June 5th event shows two flares in different places happening within a small time frame, but without a clear field line connection between active regions. Instead, the field lines between the two active regions, 14455 and 14457, are open. Looking at the images of the area of open field lines shows there is actually a coronal hole between the active regions. So you can see in the 3D model, we have the open field lines extending outward, and then we also have, in this picture, it's the day of the event. And since most of the activity is to the side, if we actually look a couple days before, that's when we see this coronal hole, which is separating our two active regions. The second event on April 26th shows similar sympathetic factors, but with a possible chain field line connection to a third active region. Looking at the visuals of the flares at the active regions 14420 and 14425, it can be seen that the middle active region, 14424, is also flashing, possibly showing a lower cost flare. And then you can see the highlighted field lines that are showing the connection to that middle active region. Here are a couple of videos of the April 26th event in the wavelengths of 131 and 304, showcasing the flares and the middle region activity. So this is our first video at 131 angstrom, and you can see these regions on the side are our made flares, and in this difference video you can better see that there's activity in between. This one's quite flashy. Again, this is the 304 one, but it's much easier to see the middle activity when you look at the difference video, so you can see that there's something in this middle active region. Looking at the videos of the April 26th event and the running differences, that the middle active region appears to be active around the same time as the first flare. This indicates that it is likely that energy flowed between the active regions along the magnetic field path. Because of this, the April event is likely sympathetic. The June event is likely not sympathetic, as the open field lines and coronal hole show a barrier between the active regions, indicating that the timing of the flares could have just been by chance and not a sympathetic event. The prediction models from before the April event show percentage chance in the active regions that flared. Taking into account the magnetic connections could increase the percentage chance in the model, creating more accuracy and certainty. So you can see that at the middle active region and the side active regions we have somewhat of a percent chance, but on active region 04 you can see that it's not above 50, even though it did have an M-class flare. So acknowledgements. Thank you to my mentor, Dr. Purvis. Thanks to Lynn and Ariana for the N3 opportunity. And then everyone who helped me with the 3D prints. Here are some sources for the stuff I talked about. And yeah.